Chen from Chemical Engineering, talking about atomic force and optical microscopy imaging on nano-biomaterials.
Okay, I want to thank you for the organizers for these wonderful opportunities. Now, I guess the thing probably will have to change a little bit in my talk. Now, my lab is in chemical engineering department, and we are dealing with a lot of nanoscale biomaterials. And sort of the grand theme of our research is that we want to find a way to integrate, this physical applied science engineering to biomedical research. And particularly what we want to do is we want to use the technology tools in nanotechnology and use them for biomedicine. And here I'm going to show you a few technologies which we have been using and how we're going to use them to study various biomedical problems. And you see the title here is Atomic Force and Optical Microscopy Imaging of Nano-Biomaterials. And atomic force, which I'm going to introduce you a bit more, is that atomic force microscopy is really a driving force for the current wave of nanotechnology. Because since 1986, we have this AFM, and people have been able to see things which they haven't been able to see in the last few decades. And so I will discuss more about it. And in our research, there are two things which we are focused on, which is one is cellular drug delivery. So we try to develop all these delivery vehicles on the nanometer scales and to target the drugs into the certain part of the body. And the two things which were most interesting, one is the anti-cancer drugs, because most cancer drugs, you cannot really dissolve them into your bloodstream. So you have to find a way to solubilize it. And once you find them, you have to find a way to target the tumor cells, and so that you can eliminate the side effects of these the tumor drugs. And the other application which we are working on is the so-called neurodegenerative disease. And particularly we are looking for, we try to understand the mechanism of a lot of informational diseases, such as Alzheimer's, such as Parkinson's, such as Huntington's, and then we try to find the mechanism for those culprit to occur in your brain, and hopefully we'll find the inhibitors. So this is the two major applications. Now, I don't see anything here. Oh, okay. So this is it? Okay. Now, there are sort of two techniques which we have been using. The first one is so-called the axisymmetric drop shape analysis. And these techniques actually was developed in my former lab at Toronto. And what we do here is this. We have this sort of droplet. We hang there in the air or in the certain sort of outside environment. And we take the image. So this is actually the setup. So this is your sample, and this is the lighting, and you have a microscope here, optical microscope, and you take the image. So once we have the image like this taken, and we're going to digitize it, and then we're going to do the edge detection, and after edge detection, we have this profile. And once we have the profile, and we do the image analysis through sort of a nonlinear curve fitting. Now, physically, this drop shape and the influence of gravity is determined by this equation. This is the pressure, the curvature, all this. And the one important parameter is that gamma, that is the surface tension. Now, surface tension is a thermodynamic parameter. It's probably one of the most important force parameter in studying physical chemistry of surfaces. Now, you may ask me how this is related to biomedical research. Well, we can use these to study the so-called lung surfactants. A lot of newborns, they couldn't breathe themselves because of the lack of lung surfactants. And if you have the lung surfactant adsorbed to these surface, say the air liquid interface, then the surface tension is going to be reduced so that you can breathe easily. So you can use these to quantify the lung surfactant behavior and find the therapy. So this is the application. Now, and I think the things related to the current workshop is that, and here we need image analysis, we need image processing, the edge detection and the curve fitting. And these things is not trivial to the normal engineers. Some probably the computer scientists will be able to help us. So this is the first thing. So this is just a quick data, and what we can generate is the surface tension as a function of the pressure which you apply. When you're breathing, you're changing the pressure. And here is the sort of a solubility, the diffusion of carbon dioxide into the aqueous solution. So this is the first technique. The second technique, as I said, which I will discuss a bit more, is that the so-called atomic force microscopy. Now, I think most of you are probably very familiar with this technique, and here just to brief it. And the key of this technique is that you have this sort of very, very small cantilever, and then you have this chip at the end of the cantilever. Now, think of this chip. This chip is very small. They are so small, and so the diameter of chip is about 10 nanometers. Now, here we go. We have a very different length scale here. Now, most people talked before me, they talk about the smallest scale is in order of microns. And here we talk about nanometers. Nanometer is the 1/1000th of a micron. So it's 3 orders of magnitude smaller. And here, when you have this such a small sharp tip, and think of that, if you have a small tip, you can move it so close to the surface of your sample underneath it. And it's so close, so it can detect the intermolecular forces. Intermolecular forces, literally 2 molecule interaction, it can detect that. Now, once you have attraction or repulsion, you see this cantilever will be bent a little bit. And so that you have the laser beam and has a deflection, and here is the photodiode. And so through these sort of a signal and transformation, you can map out your sample surface, topography, as well as some heterogeneity in chemistry. So this is the basic atomic force microscope. So the person developed it at IBM Zurich. They won the Nobel Prize and after a few years. Now, here's the example, and sort of related to our research now. We do a lot of nanoscaled biomaterials. And one of the interesting is that how we're going to see these biomolecules form nanostructures. Because this is very important. If anyone is familiar with this degenerative disease, you find out, and say, for example, in Alzheimer's patients, in the brain they have lots of plaque. And this plaque is majority formed by proteins, not just normal proteins. They are misfolded proteins. And these proteins will form aggregates. And these aggregates normally form these fibers. And here we're just showing you this FM imaging of these fibers, or the nanofibers. And here we have this so-called the sequence dependence, because we know for a lot of protein misfolding disease, and the secret probably is buried in the sequence of your peptide. Now here what I'm showing you, if we're going to change the sequence a little bit, and very minutely, you see the very drastically different nanostructures. And these different nanostructures, some of them will cause disease, some of them will be degraded without causing you any problems. Now, the next picture actually is showing the contrast or comparison. And this picture is sort of the protein which you can find in Alzheimer's disease. It's amyloid beta peptide. If you put them into the right environment, they have these sort of nanoscaled structures. And so you can see that. And here, I think I'm rushing the time here. Here is the sort of prion disease proteins. They can also form these nanofibers. And our interest is we want to understand why these fibers are formed and how we're going to inhibit them. And that's why you can find therapeutics. And here, actually, the 2 synthetic fibers we created in our own lab so that we can understand how these fibers formed. Now, the last image is that now the advantage using AFM, atomic force microscope, is that you can do it very differently from the conventional sort of a microscope, such as EM, electron microscope. There you can see the nanometer scale features. However, you have to put your sample in high vacuum. In our case, we leave it in any environment, simulate physiological situations. And here we do in the liquid situation, we can see this fiber dynamics, how it grows, how it generates the network. So if I can...
Better get to the last slide, okay?
Yeah, this is the last slide. It has to move. It doesn't move here. Oh, okay, so thank you.
Thank you very much.
Anyhow, what I was going to show you is that you'll see that fiber start from a few seeds and a few nuclei. They're going to grow this fiber network. And that imitating, to some extent, the amyloid beta, which is the disease state. You want to eliminate that.
Thank you very much.
Thank you.